Most people do not realize that the air is not transparent. We will use transparent sheets for our example. Also, we will use lighting gels for the water and lower water line. This will simulate the horizon the way it is on Earth. Each sheet should represent several miles. The key people need to understand is that the horizon you see is not the exact horizon. If there was no air, no water, or anything else, the horizon would be lower on a perfectly flat plane. People misuse the word vanishing point and perspective in the flat Earth movement, and here I will prove how it works. The first concept is air density. Have you ever driven on a foggy day? You can't see 2 feet in front of you sometimes. Or take this example of the Chicago skyline from what should have been an impossible 40 miles away. Some people ask why the buildings are cut off. But isn't it obvious? Here you can see a cloud of air. What they should have asked themselves is, why can you see the buildings at all if the Earth is not flat? Now, what is very important to understand is, air compounds. Every mile, there is more air to look through. This forms a gradient. When we put several sheets of clear plastic in front of the other, they form a wall that you cannot see through. The atmosphere is filled with oxygen, zinc, carbon, hydrogen, and many other chemicals that forms a wall of density. Let's watch the experiment in action. As you can see, the sun gets cut off from the bottom first. But that's not all. There's many things to discover in this experiment. First of all, you can see the light shrink around the sun as it sets. This is exactly what we see in real life. When the sun sets in our experiment, we see a color change, just like real sunsets. One major difference in our experiment is it's on a small scale and it's low budget. The advantage is you can do this yourself at home. We will now compare to the horizon you see daily, but before we do, we want you first to understand perspective. As you can see, things that move to the horizon get smaller and lower. However, the appearance that they are getting lower is just perspective. You prove this by looking at a long hallway. The altitude of every light in the hallway is the same, right? Some people think in the flat Earth that when things hit the horizon they diverge due to optics. And although that's a very interesting idea, we're only working with logical things that we can prove in an experiment. With air density, you can prove sunsets without fancy diverging lines, however true they may be. You can see in our experiment we have lower atmosphere, middle atmosphere, and high atmosphere. Did you know that the air gets thinner as you get higher? This is because of buoyancy. You see things that are less dense separate from things of greater density. This is why clouds float, this is why helium balloons rise. This forms a vertical gradient and gives us a horizontal and vertical air gradient. In fact, the speed at how fast things fall depends entirely on buoyancy. If you drop an item in the water, it falls much slower than in low altitude air. If you fall from a high altitude, you fall faster. When you jump from air into water, you fall fast and then slow. Now we combine all 3 ideas, and you will get this. Right at the horizon there is a 10 to 20 mile high wall of air. The wall of air depends on weather. Remember, it's a vertical and horizontal gradient. Think of it like a diagonal wall or a ramp to heaven. On high humidity, the wall will be closer. On low humidity, the wall will be further, sometimes hundreds of miles. The air compounds. Well, let's just say the sun sets beyond that wall. It goes behind it. Remember how we said that the further things go, the smaller and lower they appear? Well, right at the horizon, an extremely thin line, represented here, is the vanishing point. This is about a 10 to 20 mile high wall of air. Also, remember there's clouds as well blocking you in the way. Remember the buoyancy idea? Well, the high altitude air is thinner, so the wall is a little bit further. This is why the sun changes colors before it sets on a clear day. It gets blocked by the buoyant air, and then its bottom is cut off by the heavier air. Now you might be thinking, Can a 10 to 20 mile high wall of air seriously block the sun when it's thousands of miles away? Well, of course, and here's a diagram of exactly what you're experiencing. You can see the observer and a line drawn to the horizon. The sun gets cut off when it's thousands of miles away. This isn't to scale, but you get the idea. You can even do the math for this if you like. Draw a triangle. Imagine the horizon line vanishing point is about 50 to 100 miles away. Then you will see, even if the sun is high, it will fall into the horizon. In our experiment, what you won't see is how dramatic of an effect the air has on the sun. It tends to dilate the sun's diameter. This is why when you see a sunset, it doesn't shrink as much as it should. It does shrink, but it also dilates. And if you film the sunset from a high and dry altitude, it'll shrink a lot more. Including if you watch sunset time lapses from airplanes, you'll see the sun shrink. I also want to take the opportunity to answer some very uneducated criticisms of the Flat Earth movement. People say, "Why can't you see New York from England?" Well, you can answer them in a word: air. Also, there's questions like, "Why can't you see northern stars from the south?" Again, air. Also, let's look at ships on the horizon with this refreshed perspective. What density also affects is the water line. Look at this diagram again. Did you know that the air above the water is filled with more water vapor? Well, of course, right? Buoyancy. So that may not seem important, but it's of huge importance in optics. Imagine if I used these blue gels instead of transparent gels. Would you be able to tell the difference between the water line and thousands of these gels stacked together, compounded over many miles? Let's look at some examples. You can see here the boat is almost invisible. Here, the air almost completely blocks it. From far away, this air is dense with water and even reflects the water below. This higher waterline effect can cause boats to not be visible and even cause a slightly higher waterline occluding the bottom of buildings and beaches. Remember, over the ocean there is waves too. The water in the air sometimes causes a sparkling, wavy fractal pattern when you zoom in on it. This is why using examples such as the Bolivian salt flats, Mount Everest, and other land examples are in some ways better for proving that there is no curve. Since you also need to educate people on compounded water vapor. Also, the water line can cause boats to look like they are floating and other really funny visual effects. Now imagine looking at a sunset over the ocean and what all that air does to the horizon. Well, surely it would cause a vanishing point. Also, clouds compounded add to the long list of obstructions in the horizon. Again, for further research, you should look at converging and diverging lines of perspective on the horizon. Perhaps we can consider the curvature of the lens of our eye and even a camera lens as well to play into this. The sunset we see on the Earth matches one on a flat Earth because of the diameter change of the sun, the shrinking light of the sun, and the sun's path in the sky. However, there are already so many videos debunking a round Earth and proving a flat one, and if you have seen this video up until this point, I would love it if you would do more research on the subject. When searching for the truth, it doesn't matter if the world disagrees with you. If you are right, you are right, and the truth will set you free. Sheep follow the government blindly. Nobody listens to the black sheep because the black sheep is not in a position of authority. But the black sheep sees something, doesn't he? Science done honestly is beautiful, and hopefully I have shared a beautiful idea with you. So hopefully this video was educational. Thanks, and hopefully now we can put the issue of sunsets to rest.